So this week we're going to start talking about temperature. We brought all this energy into the atmosphere last week with solar radiation, and we allowed some to go out with infrared radiation. But there's still a lot of imbalances in the energy out there. So we got to talk about some heat, temperature, and the atmosphere, how that all impacts atmospheric circulation. So really what we're trying to define are what are the causes and consequences of heat transfer within the Earth atmospheric system. So let's define some terms first. All matter has molecules, and all those molecules move. They can have a continual vibrational, rotational, whatever, translational motion. So energy is represented by this motion. It's kinetic energy. So the more they move, the higher the kinetic energy. Temperature is directly proportional to that average kinetic energy of these molecules. So if you know the temperature, you know approximately the kinetic energy of that material, be it a gas like the atmosphere, be it ground, whatever. The temperature gives you an approximation of the kinetic energy of that stuff. Internal energy is a whole different thing. It encompasses potential energy, which we're not going to discuss right now. Heat is basically energy in transfer. So what happens is you're transferring kinetic energy between two objects. And kinetic energy always goes from a warmer object to a colder object. So where the molecules are moving faster, they tend to vibrate into the colder molecules and make them move faster. So that's the way heat is always transferred in the system. So they can do it in different ways. Many times they do it with a temperature gradient. Other times there are radiation, conduction, convection, even latent heat. So we're going to discuss all of those. But the second law of thermodynamics basically says heat flows toward lower temperature. Again, I'm thinking of downhill. I think of low temperature almost like a valley and high temperature as being a ridge. And the heat is just flowing from the high down to the low. So the bigger the number, it goes towards the lower number. We talked about radiation. You probably are tired of hearing it last week a lot. But energy comes in the form of radiation many times. Say you heat microwaves in the microwave. That's radiation energy heating up an object. The sun obviously heats an object up. And we know the Earth emits radiation back out, cooling it. So that is one form of transfer. It often occurs within a vacuum or in space. Conduction's another. Have you ever put your hand on a hot metal plate, for example, and you have to move it away or burn your hand very quickly? That's conduction. Transfer of that heat is going into your hand. So some substances are very conductive. Air is not. Air is very, very poor. Matter of fact, it's one of the least conductive substances around. So if you have air trapped, and think about it, in your house you have probably fiberglass insulation that has air particles in it that keeps the heat from moving through it. However, in things like liquids and gases, there's things called convection. You ever boil water and see the bubbles start from the bottom and move upwards and come out at the top of the water? That's convection. That's heat being transferred within the liquid. In the atmosphere, if you ever watch it, you see little sometimes cumulus clouds forming in the afternoon. That's really heat being transferred as the air is rising upwards, bringing heat up with it, and then sinking back down, cooling it behind it. So that is another way of heat is transferred in the atmosphere. Latent heat. Think about latent heat. Water vapor, the molecules are moving pretty quickly. So when they become liquid, the molecules had to slow down, right? So if they had to slow down, they had to lose heat. So heat was given off, and that's the latent heat. So when we have phase changes in the atmosphere, heat is either given away or taken in by water vapor. And there's a lot of that transfer. So if you go from a vapor to liquid, you're losing heat. If you go from a liquid to solid, you're losing heat. If you go the other way, say you have a puddle of water sitting there and the sun's baking down that day, that puddle is evaporating. What's it doing? Well, in order to evaporate, it had to absorb heat. So it keeps some of the radiation from the sun and doesn't allow it to heat the air up. So you wind up being cooler that day. A lot of times after it's been very wet, it stays a little bit cooler than it might otherwise because the ground is so wet, and a lot of the sun's energy goes into latent heat, causing evaporation. So you can actually see that in maritime climates. I live near the ocean, and one of the things we get here a lot of times is winds off the water. And our temperature really doesn't fluctuate nearly as much as you that live in West Virginia. You have a much colder winter, and you can get warmer in the summertime sometimes. We tend to be more moderated. Now, if we get a lot of wind coming off the continent, from the west, the Maritimes aren't going to influence. But take a look at San Francisco here, very close to the ocean, a lot of west wind there. You can see it doesn't get real hot in summer, it doesn't get real cold in winter. St. Louis, on the other hand, which would be more like you all, gets much bigger ranges. Here is just a sampling of all the radiation coming into and out of the Earth system. As just look at it, you can see it's really complex. But one of the interesting things is 47% of the sun's radiation is absorbed by the Earth. So that is something to think about. Where'd all the other 53% go? Some of it went into the atmosphere, 22%. Some of it's reflected back out. Some of it goes back into the atmosphere, it gets reabsorbed and comes back into greenhouse gases. So all this complex radiation balance has to be accounted for to understand how temperatures change. So when you add heat with convection and conduction, you get sensible heating, it's called. It doesn't take anything to do with latent heating into account. And this can produce clouds, this can produce a change in temperature. It is just taking two parts of the heat transfer process to see how temperature is changing due to that. Here's the sun's radiation coming in. You can see between about 30 degrees north and 30 degrees south, there's actually a surplus of solar radiation throughout the year. Then we lose. So, but north of that, there's a deficit. So this surplus, this extra energy, has somehow got to get transported poleward. It's done through air masses. It's done through storm systems. It's done through hurricanes. Tropical systems do a lot of it. They warm up the north. So all of this is why there's an imbalance, and that causes your weather. So air masses, what are they? Basically just huge masses of air that all have uniform characteristics. I'll show you one here in a little bit. So with this imbalance, that's what causes circulations, that's what causes what you feel daily, your changes in weather. And here you can see actually a daily curve. One of the things you were asked at the beginning, the very first question, and one of the first questions in critical thinking, chapter 1, was why do we heat up more through the afternoon? Well, look at this. The Earth continually surplus of radiation till about 2, 3 o'clock in the afternoon due to the sun's energy coming in, exceeding the amount going out. However, right after that, we go the other way, and the Earth really starts cooling. And actually, the most dramatic cooling occurs during the first 2 or 3 hours in the evening. And that's when the temperature will drop fast. And then it slowly settles down after that. So that by midnight, for example, you can see, yeah, we're still sending out heat away from the Earth's surface, but it's not nearly as quickly as those first 6 or so hours, 5 or 6 hours. So one of the other things, bare ground absorbs solar energy. We know that. whereas snow or ice have a high albedo. So say you had a big ice storm or snowstorm in there in West Virginia. If it occurred, you would wind up after that storm. You ever notice how bright it seems outside? You're getting all that sun's radiation is getting reflected out. So you're not warming up as fast. So a lot of times when you get snow covering large areas of the U.S., it's self-sustaining. It actually generates and keeps cold air around longer than if you just had bare ground. If you have bare ground, you wind up, even if it's a very cold air mass coming out of Canada, it can't hang around as long because it's got to dry out. So, and the other part of this is you get things like heat island effects in Washington, D.C. and all too. So, all right, so let's go from this and just look at a couple things here. So we talk about advection. I wanted to show you some cold air advection right now. It's not a lot today. I was trying to find some, or even warm air advection. And there's a cold front that's right now running through North Dakota, South Dakota, almost into Minnesota. Look on the east side of it. Temperatures are in the 80s here, 80s here, and you have a southerly wind at 50 knots. On the other side, it's 70, 75, and you have a northwest wind. So what you're doing is advecting cold air from the northwest on one side of this front, and you're advecting warm air from the south on the other side. The tighter these gradients are of temperature, and the stronger the wind is coming in perpendicular to these gradient of temperature, the greater the advection will be. And you need to have a fairly decent understanding of what advection means, because you're going to see it a lot throughout this. One of the things I want to show you too was an hourly weather forecast of temperature. And you can see here, we talked about the radiation budget, allowing temperatures to warm here during the day. But notice how fast that temperature really drops down from about 7 o'clock in the evening to 1 a.m. It drops 12 degrees. And then after that, it only goes 2 more. So it really slows down. That's that decrease in deficit of radiation. Then picks back up. It rises very quickly in the morning, and it will continue to rise in the afternoon, but not as fast. This is a forecast for you all for on Monday. And I wanted to show you here an air mass. This was yesterday, but I couldn't find a good one today. But take a look at this big high pressure. Air masses are almost always associated with high pressure. Why? Because they don't like winds moving much. If the wind's not moving much, the air can take on the characteristics of the region it's over. So you think about high pressure in Canada, it's over cold air, cold, dry ground. It's going to be fairly dry. It's going to be fairly cold. So that's an air mass. And that air mass will be eventually moving south into the U.S., depending on the upper level winds. Remember, it's three-dimensional to the atmosphere. So it's just something to learn for today. Hope you got something out of this. Let me know if you have any questions.